All right, well, good morning, everybody, and welcome to day 2 of the summer apprenticeship program. We had an awesome day yesterday, and today I suspect will be even cooler. We have a lot lined up. This morning you received the schedule, had the link to get you here, and a rough summary of what we can expect today. So I won't waste much time this morning talking about. I will give anybody the opportunity to ask any questions, any burning questions from yesterday, or any big questions about today.
All right. Yeah, I already saw that Robert already posted a question on a scale of 1 to 10. I'm going to answer that after I'm done with the introduction, because to quote Inigo Montoya, when you think or hear the word computer science, then I don't think that what it means, what you think it means. So we'll clarify a little bit of that. So yeah, but other than that, let me, I think, introduce myself, and can I share my screen with you guys? I should
Yes,
be
so
able
you
to do that,
should
right?
be able to.
Hold on, I need to actually get to my okay, where did my mouse cursor go? Okay, all right, let's do this and share. Actually, yeah, this one. All right, so you should be able, hopefully, to see my presentation. Let me go back to the intro slide. One of the things I hate about Zoom is that it actually hides what students see. So I just assume that you can see right now what's on thing, right? You should be seeing the introduction to computer science. Richard, can you confirm that you see the slides?
Oh, yes, sir. We're good.
Yes, I can.
Okay,
I can
okay,
see
good,
the slides.
good. All right. So welcome everybody. My name is Jens Hanneman. I'm associate professor here for computer science at Kentucky State University. One of my partners in crime is also logged on, Dr. Mighty. And I'll let him introduce himself after I introduce myself really quickly, so that you know who we are, where we come from, what our backgrounds are. So yeah, let me first start out, however, before we do the personal introductions, to talk a little bit about the program itself. So we're a classic computer science program, and we have 4 concentrations that you can take. That caters pretty much to everybody. Robert was already saying, well, how difficult is it? Well, we make it relatively easy for you to figure out at what level of difficulty you want to be in the program, because that's what the 4 concentrations really represent. So we have probably our 2 most popular concentrations. The first one is where I'm mostly involved in, and that is the video game development track. The second most popular is probably the cybersecurity track, but they're pretty much on par. Cybersecurity really has become a very hot topic over the last years. So cybersecurity is a big one. The third one is information technology / networking. And then the fourth one, and coming back to the difficulty question, that is what traditional people would consider the most difficult one. We call that the math track. That's your classic computer science track that prepares you for graduate school, really. This is the only track, and this is probably good news for many of you, that it's the only track that does require calculus and the calculus-based natural science classes like physics and such. So all the other classes, certainly not as an admissions requirement, require calculus, and we do have a little calculus / linear algebra math class that everybody has to take, because otherwise you will not be able to survive anything like networking or operating systems or computer graphics. But those are the four concentrations that we have. We're a small outfit, as you probably know. Jeremy has probably pitched it to you this way. Our classes are small, which again is good news, and I take a great joy in that. I used to teach at the University of Kentucky, and I was doing some of the lower level computer programming classes with like 200, 250 students. So I just love the fact that we rarely ever have a class larger than 15. We're all capped at 20. So we really have time to cater to your individual level of skill. And if we figure out that you need extra help in a topic, we'll be more than happy to give it to you. Likewise, if we figure out that you're a pretty smart cookie and you need a challenge, we'll be able to throw that at you. We've got tons of opportunities for undergraduate research and all that stuff that goes along with that. So that's one of our strengths, and that's one of the main reasons why I'm actually here. So that's the program, and feel free to jump right in with any questions on that if you want to. And if not, we're going to, of course, have the opportunity to talk about more things down the road. As for myself, so as I said, my name is Jens Hannemann. I'm originally from Germany, and by training, I am actually a electrical engineer. My research areas are actually computational electromagnetics, high performance computing. I came as a postdoc to the University of Kentucky working on things like microwave integrated circuits. That's the stuff that's in your cell phone. Radar cross-section computation for stealth fighters. So we did a lot of work for the military, and ultimately I got involved in a project that involved a combat simulator, urban combat simulator for the US Army, which was really a bad as huge immersive video game, which led me to Kentucky State, because about 10 years ago, Kentucky State decided to get on the bandwagon and to offer a video game development option. And here I am. And I was happy to jump ship, never look back. And I think this is a pretty cool place to hang out. One of my other areas of expertise where I also teach, of course, then is software engineering. That will be the introduction also to Dr. Mighty. And another thing, of course, because I'm an electrical engineer, you will take all the lower level classes with me in terms of like hardware, operating systems, this kind of stuff. So that's myself. I'll hand it over to Dr. Mighty real quick so that he can introduce himself.
Good morning. I'd like to welcome everyone to Computer Science Day. So I'm Dr. Richard Mighty, and one of the other professors here at the Computer Science Department. So I've just finished up my second year. So I'll be starting my third year this fall. So very happy to be here, really like it. As Dr. Hannemann said, our classes are small. So you can ask as many questions as you want, and you can get as much help as you want. So it's really a great environment, and I really like it. So my background is primarily industrial. So after I had finished my undergrad, I spent a decade at IBM, IBM Global Services. So I worked on the server side. So I developed codes, programs for server performance, for capacity planning. So that's kind of my background. Then I did some consulting, worked on aircraft software for safety systems. I did that as a consultant. So, primarily all my development was in C++. And our courses that you will be taking, so I teach our 108 and 109 courses, which are also in C++. So after consulting, I joined the University of Kentucky, where I had graduated from with my undergraduate degree. I was working there on their digital preservation and also data analytics. I had a few projects I was working on over there. while I was teaching part-time and finishing up my PhD. Then I had a visiting professor position at Berea College, and then I came here. So I'm very happy to be here. Also, I see one of our other professors, Dr. Shen, has joined us, so I'll hand it over to her to introduce herself.
Thanks, Maddie. Okay. Good morning, everyone. My name is Chi Shen. I'm the computer science professor at Kentucky State University. Welcome to Kentucky State University SAP Summer Camp. So as Jens Henman introduced, and our computer science program has a lot of concentrations and focus on different areas because we have a very diverse group of professors with various research background. Yeah, so you can see Jens Henneman has an engineering background, and Richard Matt has a security and other industry experience. And my research background focus on now data science and data mining, so which might be useful for the in a lot of areas in agriculture, medical center, and the security anywhere. So data science, I know, is a hot topics right now, as along with the cybersecurity. So if you want to pursue these two areas, so the Kentucky State might be your choice. Okay, so we have a very talented group, and I hope you can join us. So, and also today we are going to focus on these two areas, data science and security. So hopefully you can enjoy of today's presentation. Okay, so again, welcome to Kentucky State University, and I'm glad to meet you all on in virtual environment. Hopefully we can see you in person next year, right? Yeah. Okay, so I don't want to talk too much, so because I want you to direct it to enjoy our presentation.
All right, so let's jump in and clarify first of all what computer science is and what computer science isn't. If you could give me a show of hands here, who of you actually thinks that the subject of study of computer science is computers? All right, I see 1 out of 3. Okay, so the other two either know better or have sniffed that out as a trick question. And Robert actually says, well, isn't it more of coding? Exactly that, it isn't. So there's one of the most famous computer scientists of all times is Edsger Dijkstra, who's the Dutch guy, eventually ended up at I think Texas A&M or one of the universities in Texas, and his algorithm on how to find the shortest path in a network from path A to path B is really the foundation of the internet. We couldn't have done it without Dijkstra's algorithm, really. And Dijkstra was an interesting guy, and so one of his most memorable quotes really is that he said, and this is undoubtedly true, that computer science is no more about computers than astronomy is about telescopes, which means that they're awesome tools. They are what we use in what we do in computer science. I have a very good friend who is the director of the Student Observatory over at the University of Kentucky, and heck does he know a lot about telescopes, but that's not why they're doing it, right? Astronomers study the universe using telescopes to figure out where we came from ultimately. So here it's about the same thing. In my native language, German, we actually don't use computer science as the word for what computer science is. We have an English word for that as well. We call it informatics. So the study of computer science really is it's one of the greatest misnomers of all time. So the area of study of computer science really is information, and we use computers to detect patterns in information, to extract knowledge from information, to transform information, and to present information. That's what this is all about. And that is actually good news, because if it were just the coding, or if it were just about executing some algorithms, then it would be number one, pretty boring. And number two, your job safety would not be very high, because if it is so simple, that goes back to the difficulty level. If it were so simple that a computer does it, well, then yes, computers do it, putting you out of a job, right? So as I said, so I'm an engineer, right? I can build a computer, but nobody builds computers and designs computers manually anymore. We let computers design. So we give the computer, the program that we use to design the computer, a description on the instruction set architecture, and then we have the computer design a computer that will then eventually be handed off to yet another computer that creates the lithography masks for the chips, and then we have yet another computer that will etch all of that into silicon. So it's kind of the interesting thing, but that doesn't mean that humans are useless, right? We just move what we do to a higher level of abstraction, and that is what computer science is really all about. To demonstrate this fact, let me show you something. And this example is about 300, well, not quite 300, 250 years old. And it's still relevant today, because you will see that what I'm going to show you now is exactly the way of thinking that you need to ultimately be hired at Google, because this is pretty much exactly what Google is all about. So the story is about a German mathematician, well, not surprisingly, given my background, right? Carl Friedrich Gauss, one of the greatest mathematicians of all time. And you see here, when we still had our own currency in Germany, it was so important that we actually had him on our currency. Well, he was a very smart cookie, right? But he was also already a very smart cookie as a child. He was a child prodigy when it came to math. So naturally, in school, in math class, he was easily bored and he got unruly. So the teacher eventually said, you know, Carl, I've had it with you. Go back into that corner there and just add up all the numbers from 1 through 100. And of course, the teacher assumed it would take him forever to do that. And she said, why? That's 5,050. And the teacher was stunned, eventually did the math and figured out that was correct. Does anybody, here, before I go further, know the story and the trick he used? All right, good deal, because sometimes you get that, depending on your math teacher, of course, right? This is a very popular story in math class, but it shows you exactly what we need and what the skill set we try to instill to you as computer scientists. So let's figure this out. So what Gauss had to do was he had to sum up the numbers from 1 through 100, right? So on the left-hand side here, right, you see actually the shorthand notation for that. Right, but it's really a shorthand notation. We do 1 plus 2 plus 3 plus 4. And as the numbers get larger, of course, the whole thing gets more tedious. So in order to do this, you have to ultimately execute 99 additions. So that's why the teacher thought this will take forever. But not so. There's a trick, and you can exploit patterns in the whole thing. What Gauss noticed immediately was the following. So let's check this out. So if I do 1 plus 100, right? So what is that result? Right? It's 101. All right, let's do the next thing. 2 plus 99. That's also 100, right? Or 101. And so it goes all the way down to 50 plus 51, which is also 101. And then all you have to do to figure this out is ultimately, well, how many of these do I have? Well, I have 50. So 50 times 101 is the 5,050 that Gauss then just did in his head, because this is simple arithmetic, right? So that's the trick. And this thing of detecting patterns to make a tedious task run a lot faster and make it a lot easier for you. And I'm going to show you this in a second in an actual running program. Is really what computer science is all about. This is the stuff we're looking for. This is what pays the big bucks. Nobody pays you big bucks for writing a program that goes through and adds up all the numbers from 1 through 100, right? But if you can actually write up, and we'll see this goes further than that, but if you detect the pattern, you can do it faster and considerably, fundamentally faster. And we're going to talk about what that means. That's what computer scientists do, and that's what this is all about. Okay, so Gauss noted that, right? So, and here is ultimately the whole thing written out. But the cool thing is this not only works for 100 numbers, this works for any number, right? So I can actually take, oh, come on. My iPad is giving me trouble here. Here we go. So I can actually take any sum to any number n up here and do this. And if I do the math correctly, I end up with a simple formula saying that if I add up all the numbers from 1 to an upper number n, the result will always be n times n plus 1 divided by 2. So that is that's where it's fundamentally different. Because let's check this out. Instead of having to do 99 additions, or in the case of n minus 1 addition. So let's say I want to take a million numbers, right? So I have to do roughly, give or take, 1 million additions. The other formula never changes. It's always 1 addition, the n plus 1, 1 multiplication, n times what you just computed, and 1 division. So it's 3 operations, and that you'll have to do, and that's it. No matter what n is. So, and this is where it's fundamentally faster. We have a term of that in computer science. We call that computational complexity. You just basically count the operations that you need to take to for a problem size of size n, and then you leave out the details, right? So roughly, adding up 1 million numbers takes 1 million additions. So we call this O of n, or n, or O of 1 million. And ultimately, for any number of n, we call this O of n, and we call this linear complexity because twice the problem size takes twice the work. That's why we call this linear, because there's a linear factor involved here, and we just disregard all the other stuff. However, Gauss's method is a little bit different. This computational complexity is constant. Regardless of the number n, it's always 3 operations I have to do. And we skip the 3 and we go just right to 1 and say, okay, well, for computers, that really doesn't matter. We call this O of 1, or we call this constant complexity, because the problem size doesn't matter. And this is what Google really is all about, because Google has today probably whatever 1 trillion documents in their search index, right? 5 years from now, they're probably going to have 1 quadrillion, so 1,000 times more documents in there. Yet, when you ask Google now, just as you have asked Google in the past, or if you ask Google 5 years from now, Google will still give you the answer to your search in under a second, searching through all the documents that they have. And they do this by being extremely smart about it, and by applying basically the same principle, where they say, well, instead of a linear search through all the documents, right, going from document to document, which would take you, let's say, half a second or a millisecond, even if it's a millisecond per document, right? So you have 1 million documents. Searching 1 million documents already would take 1,000 seconds. So if it were linear complexity. So Google's smart about it. They don't do that. They come up with ways to keep the search complexity constant. And this is, of course, why when you work for Google, you get paid pretty well, because that's what they do, being smart about these things and trying to, and however, when I say smart about this, and this is what we're trying to do with you guys is none of this is black magic, right? There are a couple of standard tricks that we all know that we will put in your toolbox to say, okay, here are the standard tricks to do that. And if the standard tricks don't work, then of course you got to think a little bit harder, but you can go a long way with the standard tricks that we teach you in our program to do stuff like that. So again, this is what this is all about. So let's show this. And the cool thing about this then is that, okay, programmers, somebody initially asked about the coding part, right? So when you write code, you tend to brute force things, right? So I have to add up 1,000 numbers. Okay, I'm just going to write a loop to do that and be done with it. And that's actually not bad. Hard computer scientists like Dijkstra will immediately go and say, I don't want to do this. There's got to be a faster way to do it. And then they will do it and come up with some probably relatively complicated way to do things that are fast but complex. And in the middle, that's where we sit as normal people. And I like to call ourselves, well, somewhat normal people. We're all a little bit brain damaged. But engineers really is what they're doing there, is to figure out, well, we're going to brute force it first, but when we figure out that there's it's not fast enough and we cannot buy a faster computer, you got to also take economics into account, then we have to start thinking about how to be smarter about it, and then apply first our standard toolbox. And if that doesn't work out, then we start thinking longer and harder. So that's pretty much the whole process. So let me show you how this works. I've written a Python program. The Python program is in the slides, but I'm going to actually share something else with you guys now. There's a relatively cool development environment out there that you can use without having to sign up, although signing up is free, called Replit. It's an online coding environment. So let me share that with you guys. So you should be able to see that now. And so on the left-hand side, you see a program I wrote that does exactly that. So what it does, it actually asks you for a number. And of course, first, we're going to add in the 100. Can you guys read this, by the way? Is this large enough for you? All right, I assume it is. Then here is the brute force method. So I start out with the result of 0, of course. And then I just go through the range of numbers, and I add them all up individually. And then I just basically measure the time and print out the time, how long it took me to do that. And then I'm being smart about it. There's no loop this time around. Here, I directly compute the result using Gauss's method. And again, print out the time this took. So forget about the details. The important part is now running this thing. So I run this thing. And let's first go with our 100. You see, well, this is running on a computer in the cloud, but even cloud computers these days are blazingly fast, right? So interestingly enough, what you see here is that 3.5 times 10 to the minus 5, so that's 35 microseconds that the loop took. Gauss's method already was 10 times faster. That's 3 microseconds. Let's do this again, because you'll see that there's considerable variation in these things, right? Now, 51 microseconds versus 3 microseconds. This all depends on, because this is not a computer you own, it's in the cloud. God knows what goes on else on it. So it's all a statistical thing. But the important thing is now, if I take 1,000 numbers, so 10 times the problem size, you will see that the first number is going to creep up. This is now 225 microseconds, roughly, again, roughly 10 times slower, right? Because it's 10 times more work to do it. Gauss's method hasn't changed at all. Let's go for 10,000. And you'll see numbers creeping up again. So let's do 1,000,000. And then now we're starting to really get into territory where he takes even a modern computer, right? So 1,000,000 already takes 310 milliseconds or 0.3 seconds, right? And the second number doesn't budge. That's exactly what we're looking for. 10,000,000, of course, brings me into 3 seconds territory. Hold on, I need to enter 10,000,000. Hold on, 10, okay, 1, 2, 3, 4, 5, 6. There we go. So now it really starts to bite us, right? 3 seconds versus still my 4 microseconds. And of course, if I would crank that number up, the first number would grow linearly with it, and the second number would just never budge. So that's really what it's all about when we talk about computational complexity. All right, let me go back to the presentation and wrap this up, and then share my the screen again. All right, so if you download, Jeremy put the file into the chat. There's also a link to a GitHub repository. GitHub is one of the main ways we distribute code. So I've created a GitHub repository that you can get it from there as well. So you can study the code. I said this is Python is our first programming language that we teach you in Computer Science 107. So you'll get more of where that came from. So yeah, but the whole point is indeed that there are problem classes out there, and linear complexity isn't even the worst. There are problems out there, which you will see when we start talking about cryptography as well, that are much, much harder than that actually grow exponentially as the problem size increases. Right, so linear is already a pretty darn good case, but we'll see all that. But the whole point is to detect these patterns and to make things faster is something that we do a lot in computer science at all levels of abstraction. But at first, there's really nothing wrong with letting computers do their thing. They're fast, they're powerful, they're cheap, and only when you can buy a faster computer that's within your budget, then you can start to think. So, but that's good news nevertheless, which means that 80% of your day is smooth sailing because you got a good toolbox, you got fast computers, you can solve problems really quickly. And then for the 20, it's the classic 80-20 rule, right? For the rest of the 20%, this is where you have to apply your brains, which will also equip you for, but this is really then also where you earn the money that is in your paycheck. Again, let's summarize the whole thing. So number one, computer science is really mainly not about computers. We do some of that, of course, right? But they're tools, but that means you still need to know about computers. I'm gonna make sure that you do. A little thinking goes a long way, as well as I said, we're gonna equip you with a mental toolbox for the whole thing. The Unix philosophy is really a great way to think about these things, but let the computers do their thing, brute force it whenever you can. But when you run out of time and money, that's where, again, you have to start applying your brains. The journey we'll be on is not easy. Coming back to the difficulty question, we have different levels of difficulty in the program, of course, but at the end of the day, all of you guys will have to go through the core computer science curriculum, of which this kind of stuff is a very big part. It's work. Sometimes it's tedious work. It's like learning an instrument. You have to put in the work to do beautiful stuff, right? But at the end of the day, you will rarely find a more satisfying career because you can literally create something out of nothing. And that's pretty much unique to computer science. The Wheaton quote, when you click on the link, it goes to a very nice YouTube video where he calls himself a nerd. I like to more call ourselves geeks because nerds can't talk to people. But nevertheless, on why it's awesome to be in the field that we're in, just because of the opportunities that we have. But the one thing is clear: you cannot succeed in this field without having a love for it, which we hope to instill in you guys, because it really is just freaking awesome to create large, complex software systems pretty much out of nothing, and to have a computer do what you ultimately wanted to do. There's hardly, for me at least, and I guess for my colleagues as well, there's hardly anything better. All right, so with that, I'll conclude it. And if you guys have any questions or comments for any of us, then let's hear it. All right. No questions at all so far, except for that one in the chat that I hope I answered by now. Okay, so Jeremy, how do we go about this? Or Richard and Chi, do you guys want to take over, or should I? Because I know that the schedule that Jeremy sent out said that I was going to continue, but I can hand it off for you for a break, and then I can come back later.
Yeah, either way is fine. Who's next? I
Yeah,
think Dr. Shen is next.
I can. Yeah, I can do. And then you take a break and then you come back. Yes.
Yeah. Okay. Yeah. That'll be fine. Okay. Let's hear it for Dr. Shen.
Okay. Is that okay, Jeremy?
I will stop my sharing.
Share my screen. Let me share my screen. Okay. Okay, share my desktop. And let me share my entire desktop. Okay. Okay, so can you see my screen now? Can you see my screen now?
Yes, I
we
can
see you. Yes.
Oh, okay. Yeah. Okay, so mine is very quick, and I just want to give you some small hands-on activities for today's my presentation. So as I mentioned before, so my area is data science and data mining. One of them is image processing, which is a very another popular topic in the real world right now. So today I just focus on facial recognition. I know there are so many software algorithm available, not for free, most of them not for free. Okay, so, but I find some demo software so we can practice a little bit today. Okay, I only give you 30 minutes. I only have a 30 minutes, very short hands-on activities. So you probably already know what's the facial recognition. It is just let me minimize this. Okay, it is a biometric technology that uses distinguishable facial features, okay, to identify a person. So this, you already know what it is about, okay, but it has a lot of application areas. Let me see. Okay, so there's some, always the good technologies can bring you more goods part, but also can bring you bad part, right? Inconvenience part. So let us talk about pros and the cons about facial recognition. Of course, this is use facial recognition can make your safety and security, right? We can uncover the criminals. You will see a lot of security camera can capture people, can capture, provide information about the criminals, and also can find missing children and find out the matching missing persons, and also can security at the checkpoints, at airport, and also at business stores and those kind of things. Of course, the facial recognition technology are very useful. but also keep in mind there's some cons as well. Okay, so your personal identity may be available for the public. So again, I know most of you young people, especially the young teenagers, they like to take photos and post them on Facebook, Instagram, and other social medias. Okay, but keep in mind those social multimedias will capture those information, and those information will be automatically tagged the people in the image. Okay, so whenever your photo post on the social media, your personal identity will be available to the public. Okay, so be careful about that. Okay, be careful about that. All right, so I'm not going to talk about those kind of things, but I just want to introduce the software in facial recognition, and just very brief concept. Okay, so first one is detection. In general, the facial recognition involve 3 main steps. Okay, first one is detection, which is in the process of finding the face in the image. So we may have a lot of photos, and in the photos, they may have multiple peoples and also different objects, right? So we want the first step is to find out the faces. So separated people faces among the objects like tables, chairs, and cars, and something like that. Okay, so this is detection. I have details. What's the detection about? So first step, this algorithm. By the way, if you pursue in computer science, you have to learn more about it. So draw a box around it to autofocus. So we use the dots. Okay, find a box about faces. Okay, and at this time we just figured out the face. Okay, the face, not identify the information behind it. Okay, so which draw a box, whether this is fixed into the box. This is the first step. Okay, the second step is analysis. All right, which is a map the face. This is a little bit harder. This involves a lot of computer science algorithms. Okay, so and that part is not free. If you download some algorithm, it's free. It's just very basic steps. It doesn't involve more complicated, complex steps. So the analysis is the step that maps faces. How? It's measuring the distance between the eyes and the shape of chin and distance between the nose and the mouth and so on. Okay, so this involve mathematics and image processing and computer visualization. So it involves a lot of concept there. Okay, so this analysis, this is a key. This is a key part. Okay, and if you have a better algorithm, your accuracy will be higher. Otherwise, it will be just roughly. Sometimes, if your algorithm is so rough, you may consider a table or chair, a back of chair, as a face. Okay, so this is very, very important during the facial recognition. Okay, so this algorithm involved. The last part is recognition. This is another algorithm, important algorithm behind it. Okay, so confirm and identify a person. Now we've more recognize this person is a female or is a male. And what about the age? And based on his face, and to see whether this is a mean guy, or he's smiling, or she's smiling, or he's angry, and so on. Okay, so this recognition is even more complicated. Okay, so verification, security feature on a newer, so those kind of things. This is just simple basics. And probably most of you probably already have a smartphone, and you know how the smartphone, they already have a camera, security camera, right? You can log in by using your face, right? By using your face, okay? Only your face can log in. If you use my face, even though we probably, if you classmate same girls or same age of girls or the boys, because they come from different families, so they can easily identify these two different faces. Unless you have twin. I heard of that. Okay, smartphone cannot identify twin. Okay, so anyway, so this is even more complex. Okay, even more complex. Okay, so now today, if you have a time, if I believe you have a computer on your hand, right? Let us practice this online face recognition software, so that you can have a taste about how it works. Okay, I chose these three. They have a different purpose, even though all of them can process facial recognition, but they have a different purpose. Okay, so if you have computer, let me copy the first. Let me copy the first address and post it on the chat, so you can. So you can, let me see. Let me put it, where's my window? No. Okay, let me post it right here. So can you copy this on your computer? Okay, copy this link. And I'm going to copy the second one. You can open the browser. Okay, open your browser. Okay, let me send this one, the second one, and the third one. Okay, so you can copy and paste. Okay, copy and paste on your computer. Okay, on the browser. So now you should have 3 web browser available. And also,
I've just checked the links. Yes, they do work.
They do work, right? Okay, good. Okay, all 3. Okay, all 3. You should open you open your browser. Okay, so now I have 3. So I have a 3 website open right now. Let me close my chat. Okay, the last one. Okay, last one. Okay, no. Okay, there you go. Okay, so you should have a 3. Okay, 3 online version facial recognition. So let us do one by one. Okay, let me tell you what it is. Which one do what kind of. First one is called a beta face free online recognition, and click old demo page. Click the old demo page here. Click that part. So you should have this page available. Okay, let me pause a little bit and make sure you're following me. Once you have this website available, you should make sure your computer have some pictures, okay, for you to practice. Okay, this the first one is called a beta face. It focuses on the face. Okay, only can identify the people. Okay, only for the people. So now, because you know, public people will be more famous than your personal, right? And will be easy to do some practice. So I'm going to use some public people's image, like a president. Okay, like president. So because we can search from the internet. Okay, easily find out a match. I try to use my photo, and there's not much matching because I really post my image on the website. Okay, all right. Do you have this page available? It works. Does this work? Any questions at this time? Do you need a moment? Let me give you a minute, okay? Because I know we have enough time. Okay, so once you're done, and you can choose files, okay? Select image, and you need to check detect image content and classify the face. The reason is I want to make sure through the facial recognition, we can identify the people's age. gender, ethnicity, and smile, emotion, and so on. Okay. And you can check more features if you want. Okay, so now let me select a photo from my photo. Okay, so I need to go to my data mining class. So in my data mining class, I created a photo for my class. Okay.
Hey, Dr. Shin.
Yes.
If they don't happen to have a picture of a face on their computer, can they just grab a random one off any Google search?
Go to the Google. Yeah, go to the Google, download one.
I just did it. I Googled Gauss, of course.
Okay.
And did a right click on the Wikipedia image and say get image address, and you can send it the image URL, and it'll do it. Yes, it's pretty cool.
Yeah. Okay. Yeah, just download it. Okay. Yeah, I'll give you a minute. So go to the Google, download any famous people. Okay. Yeah, whatever is available on the website. Okay. Go to there.
Yeah. As I said, you don't even have to download it. You can
Oh,
just right click on the image and say image address and paste the image URL into the box on the right.
Okay. Yes, you can use. Okay, that's fine. Yeah, you're right. Thank you. I just use, okay, whatever. So I'm going to use a president because this is the photo provided in my textbook. Okay, in my data mining textbook. So they just provided all the presidents, previous former presidents photos. I just randomly. So we have a Bush, we have a Clinton, and we have a multiple people. So I just click one of them. Okay, randomly. All right. So, and because they're public people, you can use an image URL. Yes, you can use it online. Okay, you can post it right here. Okay, yeah, and click submit. And you should be able to see, okay, this is result. Okay, after you upload it, and this is result. Okay, you can tell. Okay, so details about the age 60, and this is confidence. The number is 60%. The confidence. So later on, we'll let you, if you learn a data mining process, you should be able to learn this concept. Okay, of course, the higher number meaning the better. Okay, the higher number, the better. Okay. And see, this is the bold. Only 37% is bold, which is not correct. Okay, and the brown here, and this is so many detailed information. Not only that, okay, this is for the from this picture they identify one face. Okay, one face, and then the goal is we want to find out a match. Okay, for example, if you're missing child, missing seniors, and you want to find out whether we can find a similar person on a website. So you can search Wikipedia or search celebrities, any website. Okay, if you click search Wikipedia, they will probably, because he's so famous. Okay, so you will find out so many matching photos, and there is a percentage, matching percentage. Okay, the higher number meaning the better match. Okay, of course he's very famous, so we are so many. You can use a different person, and yeah, different person. Okay, yeah, you get it. This is for face. Okay, so this is for matching. Okay, and also you can search from different database. Sometimes for the police department, they may have a collect a lot of people's face. They can search, and they can map against their own database. Okay, yeah, I've seen some. Let me see. We have a message. Okay. Oh yeah. Okay. Yeah. Right. Okay. Those are good suggestions. Yes. Yeah. Mickey Mouse, okay. Yeah. Mickey Mouse is not real person. I want to do some real person. Yeah, Mickey Mouse in any other way. Okay, yeah. So you can play around on this. So this beta phase will find match, okay? And through one people's picture and find out similar pictures. Okay. Yeah. I'll give it minutes. Again, so for this is very helpful for identify the person stored in the database. Okay, so this is one of them, database. Okay, database. Let us move to the second one. Okay, we have a 3. So so you can use the same photo or use a different one. Okay, because the second one will have a different purpose. Okay, so the second one is called Coach, and the website is, let me see. It's AI. Okay, you should have. Let me close this part. Okay, you can talk to me. Okay, anytime. Okay. All right. So this is a code. This is another. Online, but it's AI involved. I would like to know a little bit about it. So this is okay. This is to identify the object. Okay, not just people's face, but also the object. Okay, based on the picture, it has a bear animal, and also has and what kind of animals, and there's a grass, there's a tree, and a pond, and so on. Okay, all right. Anyway, so you can, this is web-based AI demo, so you can upload a photo again, but this probably you have to upload it from your local computer, I guess. So what I downloaded, I downloaded one picture, a photo from Google, is a panda. Okay, so let me yes, let me upload. Okay, let me upload. So I uploaded a panda. So we have a giant panda and a baby panda. Okay, but the interesting thing is you can see, okay, how it works. All right, so now this is a result. Okay, this is a result. Now it's figured out the giant panda. So first one, this one is considered as a giant panda, which is very correct. Okay, all right, so and giant panda, and it is an animal and it's a mammal. But interesting is, see in the database, okay, because this is AI, okay, AI based. There are some, once you uploaded the picture, and this machine has been pre-trained, okay? So they're going to search this website against the data, the pictures stored in the database. So this in the database may have a dog, and the dog picture similar to this one. So therefore, this picture will also recognize might be a dog, not panda, might be a dog. Okay, maybe a doggy. So this one probably because it's a pasture, looks like a dog. So this animal may also identify as might be a dog. The second one is a panda, yeah, which is correctly identified. But also interesting thing is maybe person's black hair, because panda has a 2 black hair. Okay. Yeah. So, and this okay, so here, the things is for this software, it is AI oriented, which means you can train the machine over again. Okay, the better training and the better recognition. So you can pre-train the machine, and by pre-uploading a tons of photos and images, and set up algorithm, set up sample for different kind of objects. Okay, so yeah, this is another example. If you upload it, I did upload. Okay, so this is for the animals. If I upload it, let me upload another sample. Okay, I also downloaded a crowd of people, a lot of people, and to see if we can recognize those people. Yes. All right, so now I use this crowd of people, and this software does recognize some peoples. Okay, see, it's a woman one. We can find out a woman one, which is pretty good. Yeah, which is the truth, right? And figure out man one. Use this box. Figure out this is a man, and find it. So they based on their another features. Okay. All right, and we have a man two. Okay, and also man three, but there's some limitation. You can extend it. How many objects you want this picture to, you want this software to identify. Okay, yeah. So they have a preset number of the object they want to identify in the picture. Okay, so now we have a man five, and yeah. And they can even, maybe this is a military person. Yeah. Okay. So you can use Google to download any random pictures over there and practice. And this is this algorithm pretty good to based on my experience, my current experience, because, and that's why it is not free. None of them are free. Okay, this is a free demo. Okay, yeah, so they can identify this another woman. So how many person in the file? Okay, I'm sorry. Okay, yeah, so this is the what this is for the second one. Let me do the last one. Okay, do you need a minute? Yeah, you take time after you, okay, after you open this browser. Okay, after you open these three browsers, you can try to upload same picture. You can upload same picture and use different three browsers, three algorithms to see what's the difference. Okay, yeah, the last one. Okay, let me go to the last one. Okay, this is image recognize. This is another one, and you can drop image right here. You can drag and drop. Okay, or browse. Okay, so let me let me select the crowd people again, or let me for people. Let me find out again. Though yes, yeah, there's people, crowd people again. Yeah, there is a minimum confidence. So now you see the drop box. Okay, you see the drop box. This drop box used to identify the people's face, person one, person two, and how many confidence. Again, the higher confidence, the higher match. Okay, so you can personally set up confidence, and you can set up maximum number of objects you want to identify. This multiple pictures. Okay, yeah, you can upload different pictures and to see how it works. But this picture, okay, this is not for animals. This is for people. Recognize people's face. Okay, recognize people's face. you can upload it different people on the Google, very famous people, and then find out a match. So you can, okay, you can try. Okay, let me find another one. Okay, let's see if Panda works. So I don't think Panda works. Let me use the pandas. Okay, so it's just Gen Panda. It can recognize Panda, but not, there's no people's face. Okay, there's no people's face. Okay, I was wondering if you can download. I didn't download it. Okay, one animal and with a person, and to see how it works. Okay. Anyway, you can practice right now. So these 3 websites, 3 online for facial recognition. They have a different purpose. Okay. And you will see sometimes it matches very well, sometimes it's not. It pretty depends on the algorithm and the match engine. And those confidence and tells you this is 97% most likely it is a gender. It is a bear. Okay, it is a wildlife mammal. Yeah. Okay. So any questions? So those 3 examples just show me, okay, this is tells you, so today, what you give away for today, make sure how facial recognition software works. First one, detection, okay, finding the face, which is by using the rectangle box, okay, and then identify how, after you draw the box, you need to make sure these are human beings' faces using algorithm by calculating the distance between eyes, nose, mouth. Okay, match it for some criteria. If it doesn't match these criteria, this is not human beings' faces. Okay, so this is algorithm, and then recognize, identify the people's based on the smiling, and this is based on the hair. It is a woman or is a man, and age, those even more complex organ involved. Okay, so anyway, those are 3 steps, main 3 steps for facial recognition. And this is free software. You can practice, play for a while. Okay. Any questions?
There is a question on the chat session.
Okay, let me see. Okay, I see. Here's my chat. Okay. All right. So here's my chat. Okay. What happens with children when in the summer I wear cowboy hat and a clean shaven? Okay. Yes, yes. Okay, you can practice. Yeah, it does. Okay. Now this first one, recognize your hat, and because you mentioned about hat. First one, they only focus on the draw the box only for the face. Ignore your hair. First one, ignore your hair, okay, because that's algorithm. And then extend it, the rectangle in the larger area. Make sure you have a hair. They recognize face first, starting from the face, and calculated human being's natural distance between the eyes and the mouth and the nose. So ignore your yeah, and clean the shaven. Yes, you may have a beard, right? Yeah. So that's details algorithm, okay, for the recognition. Okay, recognition. Yeah, of course, there's a lot of complex algorithm behind it. Okay, behind it. That's why they can tell your age based on your face, Okay, based on face expression. Okay, based on face, it can tell you 60 or 30 or 20 or a kid, right? Yeah, very good question. In winter ball, yeah, makes sense, yeah. But they all focus on the face first. If you try, upload the very famous persons, and then you search use the first one beta face, you can find a very similar person. Maybe not this a very similar person, but may not be the exactly same person. Both all the people has beard, okay, or mustache. Yeah, you're right. So, but there's so many complicated algorithm behind it. I don't want to cover too much. Okay, yeah. Oh yeah, probabilities. Yes, see, okay, the better algorithm, probability. That's what, how to adjust the algorithm. Okay, how to adjust the algorithm. So all the algorithm you have to measure it. Okay, whenever you debug an algorithm, you have to provided the probabilities. We do not call probabilities. We call the precisions, right? The accuracy, the data mining. Always, any algorithm, you have to provide accuracy. Okay, and sometimes confidence doesn't mean always correct measurement. Yeah, the accuracy. You have any data mining algorithm, you have to provide accuracy. Okay, and use a training data set and a testing data set, both data set.
And the benchmark here isn't really 100% because humans are not even 100%. Many times AI algorithms these days are actually already better than humans. You see the 80%, but you also don't even know what is that compared to human, where a human may be 60%.
No, because that's why we use we have to divide the data into training data set and a test data set. So those data set, we already know the result. Okay, we already know the result, and to see what that's why we use this existing result to measure accuracy, right? The accuracy is based on we already know the result, and then we can track this algorithm to apply to the unknown data, unknown images. So yeah, so data mining, when you train a model, you always starting with the known data set first, right? And partition the known data set into training, build a model first, and then use another part of data used to assess the model. So we know the accuracy is a correct accuracy because we know the result. And once we have this to multiple cross validation multiple times, and then we can confirm, okay, this is good enough to apply to unknown data set.
Yeah. Dr. Shin, how easy is it to expand, like to say create a new little database for less famous people, like within the school, for example,
yeah.
50 people, could you still access these algorithms to kind of process your images and then give you whatever result so that you could then, identify one of the faces in a new picture?
Okay, yeah. Actually, okay, so all three software I just presented here are not free. Okay, first one, they are not free. You have to buy. Okay, you have to buy. But one thing is for the code for this software. For example, for agriculture, I can buy this AI machine and train the model. I only use this machine to train my crop field. Okay, for my different kind of crop, different products. Okay, like apple, different kind of apples, and store them into the database. And then we can use and train this model can only identify the apples, different kind of apples. So this is AI based image recognition has high demand because you can train your database, you can train the machine, and you can not only for the people's face, you can to any kind of objects. And beta face and image recognition only for people faces. We have very decent algorithm for human beings faces calculations. okay, calculations. They have you sure you can do that as well. You can build your own database and compare your data, compare your image process against your database, the image stored in the database, and find out a matching. Is that what your questions? Did I answer?
Yes, ma'am. Yes, basically. Thank you. Thank you. So if anybody would be interested in doing something like that, I don't know, would that be something feasible a student could tackle? I could just imagine they could go in the school and get access to all the students' profile pictures or whatever. And then I maybe not thinking about whether that's a good idea to do or not, but as far as a technical challenge.
This is the classical stuff you have to get clearance from the internal review board.
Sure, yeah, but just to get the pot stirring on the different ideas. But I like also that you say it's not just faces. It could be anything, particular land covers and satellite data or whatever. So I just want to add, right here that this, we're going to be talking next month more about the environmental science stuff, and of course computer science is really central to that, because those are the tools that we use as well. But anyway, yeah, thank you very much for that.
Yeah, and also in my class, okay, I'm going. In my class we use Python. Now this just use Python, okay, and we can use the image process. Can recognize people's image. We can take a picture for each student. Pictures if they want. Okay, we didn't do that. I still use the public person image photos, and can find out a match. Okay, this person matched with the existing images. So we can use Python to. We don't have to use this software at all. Use Python. That's all. In my classroom, if you come to Connecticut State University and take data mining classes, you should have experience to run the code. Yeah.
Yeah, there's also plant recognition, I believe. It's like if you take a picture of a plant or a flower, it'll recognize what it is. So yeah, that may not require our IRB.
Right.
So.
Right. Yeah. If you just prod, just product from the farm. Yes.
Right.
But that's an interesting point, because Dr. Shan did mention in the beginning ethical concerns, and this is how in research we actually make sure that people are not being harmed by this. Right? Yeah. This is all, if we do experiments like that involves people, then these people have to have given informed consent. There are review bodies that make sure that all of this is ethical, and so on and so on and so on.
Exactly. Yes.
Yeah. But also,
Dr. Shan, could you share any examples maybe recently? Because I know this has been pretty hot recently with the protest and the movements of people going on. Anything that you want to share that is kind of happening, any angle that you want to look at it from, or maybe some controversial new uses that maybe law enforcement's doing, for example, to monitor people using this technology?
Yeah, well, I didn't go that far. Okay, yeah, I cannot give you presentation. I cannot do that at this. I didn't go that far. Okay, because my focus is only for the image processing. For my data mining classes, a couple of students from agriculture department, so they really want to know the how to do image processing. So maybe on the field. So we focus on the crops and the farms. Yeah. I didn't want to focus on it.
Sure. Yeah, no problem. Thanks a lot.
Yeah, but that's a good point, Jeremy. I mean, yeah, it's being used by law enforcement. I think in Europe it's been used for a lot longer, in other countries that they use. I mean, there's also there's an ethical perspective on that as well. That but it's also helped in other ways, like you recognize people's patterns, that the way they walk. I mean, all this data is personal information that's being collected.
Yes.
So yeah, there is also, that should it be collected or should it not be collected? So things like that. But yeah, you do bring up a good point.
Yeah. So student, be careful when you upload your photo. People can know you, recognize you. So be careful when you use the social media. Yeah. Yep. Well, I think I used up my time. Any other questions? Okay. Yeah, I think I run up my time. So So you're welcome to contact me if you have further questions, okay? So I will turn over to next presenters, I think. And who will be the next? Let me stop sharing my screen. And who will be the next?
Jens, do you want to present? I can cover the lunch hour, that's fine.
Yeah, okay, let's do this. All right.
Y'all are free to run the schedule like you like. We would be coming up on that blank, but if your plan is set just so that you just want to push on through, that would be
Yeah.
fine as well, and you could just wrap it up, earlier than the projected.
I mean, this shouldn't yeah, this should take about half an hour or so, and then we can have a lunch break, I think, and then come back.
Very good. Thanks, sir.
Do we have a lunch break, or
yeah, we're happy to. We have it loosely in the schedule from a 12 to 12:30 time, and that's just to accommodate some groups, but everybody's all over the place with their own individual schedules. So it's whatever works best for your, for what you want to get done today is perfectly fine.
Okay. I'll pick up after the lunch hour.
Okay. All right. So then let me do this, and so let me go back and actually, all right. So what Dr. Shan has presented is at the heart of the thing, extremely complex. As you can see, computer scientists are pretty good of like packing that complexity into a simple package so that normal people can use it, which is part of our job as well. So, and I'm gonna take it down a notch again and going back to basics. We're going to implement one of the lamest cryptographic ciphers that are out there. So let me post a couple of links here. So the first thing, if you want to follow along, this is a link to a Python development environment. This is pretty much what you'll be seeing here is pretty much something that you would code up towards the end of Computer Science 107, which is an introduction to programming course with Python. And as you'll see, it's pretty straightforward. So if you click on the link, it'll open up pretty much an environment that you'll see here. Let me actually share my screen. I should probably do that as well. And all right, so and it should get you into a development environment that you've seen before here. So this is pretty much what it looks like. You have an empty Python file on the left-hand side, and then you can run it and see the results in the right-hand side. I'm going to show you how this works in a second. But what we're going to actually implement here is basically a good old decoder ring or cipher wheel. These things used to be in like cereal boxes back when they still had toys in cereal boxes. So you can click on this link here, and this implements what in cryptography is called the Caesar cipher. And it's a very, very simple thing. The first thing that you do is you apply a code to your alphabet. So here you got the letters from A through Z, so 26 letters. You assign the number 0 to A, 1 to B, and so on. When we associate numbers to letters or other symbols, we call that a code. This is a very simple code. We have more complex ones these days. The current system that we use to basically encode pretty much all characters known to mankind is called Unicode. Then you can manipulate these numbers with, well, math, right? So you can add and subtract, for instance, in this case. And this is exactly what the Caesar cipher does. So it basically picks a secret key. And in our case, the key is a single number. Now let's pick 3. And if I pick the key number 3, then what I do is I rotate the wheel really 3 numbers to the right. And now you see that the A is being mapped to the D. B is, I'm sorry, okay, well, they do the mapping actually the other way around. Okay, so I'll move it to the left, sorry. But ultimately you'll see it really doesn't matter which direction we rotate in. So, and I already said it right, I rotate to the left, I rotate it to the right. Anyway, so now you see what now is an A now becomes a D, because 0 plus 3 in the original code is the D, right? And then B becomes an E, C becomes an F, and so on. And that allows me to write up a secret message by doing these substitutions. And that's why it's called a substitution cipher. This is extremely lame. Even back in the days, this is called the Caesar cipher because the Romans used it in the Roman Empire. And this was really mostly also to prevent the messengers and the lowly folks from reading it, because even back in the day, intelligent people had not much of trouble breaking these ciphers, because overall, as you can see here, right, we have a key space of 25 numbers, really. 0 is trivial. So you really only have a key space of 25 keys that you can try. So coming back to brute force, right, you can easily crack this thing by brute force by trying all the keys. Of course, modern systems are nothing like that, but surprisingly, however, they're still like that, because we still use substitution along with scrambling, really, which is swapping of elements, as the basis of all modern cryptographic systems. If you look at how the advanced encryption standard, or AES, works, it's really not that different. It just does this a lot more times with a lot more sophistication and a much larger key space. So this is basically what we're trying to implement here. Well, that means that, and one of the things that I will actually add in here, because traditionally, when people in the olden days wrote secret messages, they did not consider the space between words a character. So they didn't encode it, meaning that they wrote the message without spaces, and you had to figure out the word boundaries yourself, which with human language isn't too hard to do. I'm going for convenience here, and since we're using computers, I throw in the space as the last character, so our alphabet will actually have the space in there, so that we can incorporate that and have easier readable messages. Which means that as far as, oh, by the way, and this is one of the first chapters really in this free book by an honest-to-goodness cryptographer, L. Swigert, who is the author of this series of free books. If you go to the whole website and went with Python, I use this book in my classes a lot because they're well written, they're free, and as far as this one goes, the guy is was an honest-to-goodness cryptographer. He used to work for the NSA. This is really kind of nice. Okay, so the first thing we need is an alphabet, right? So let's do this, and let me give you a little bit more size here. I hope that this works out well readable for you, right? So let's come up with a variable name here, alphabet, and this is just a symbolic name I choose for now. What in Python we call a list, let's or more accurately, this is actually called a tuple here, but that's really not important. So I'll put in my alphabet: A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, Q, R, S, T, U, V, W, X, Y, Z, and with good measure, I give it a space in the end, right? So this one here signifies the letters that actually do make up my my alphabet, and I actually that's that. And so that's the string that contains my alphabet. And let's just print this back to us so that we are getting this. Your alphabet is, and then just print the alphabet. And I forgot to start the quote for my message. Okay. So that gives me my alphabet. And all right, so let's run this right now. And you'll see that, yeah, my alphabet is there. I don't see the last space because, well, it doesn't really show up there, but that's fine. So one of the things that I want to know, because it determines my key space really, is how large is my alphabet. So, and I can do this by just saying the length of my alphabet is, in Python, actually gives me a way to figure out the length of my alphabet by using what we call a function that I pass an argument in. So here I just pass my alphabet object into the print statement here, and it should give me the length of my alphabet. If I run this, now it tells me I have 27, which if you do the count, of course, that's 26 plus 1 for the space, which doesn't show up there. So, but we know the space then obviously is there. And I have a typo in there, of course. So I'm going to fix that. All right. So now comes the a problem with the code, right? So we need to actually assign numbers to the letters, but it actually is already pretty cool because my alphabet is really a string of characters, and I can actually tell Python, for instance, to give me any element out of this thing. And this is the nice thing about Python in itself. Once I run my program, the thing just stops there, but I can actually try things out live so that I can play around with the thing so that I can decide what to do next with the with my program. So here I can do this one here now and do an alphabet. Alphabet. And then I can ask Python to give me back, let's say, element number 4. And lo and behold, Python actually gives me the E, which according to is a little bit counterintuitive, right? Because E is actually the 5th letter of the alphabet, right? A is 1, B is 2, and so on. Except for one thing, if you go back to the code wheel, which is right here, you see that in computer science, almost all programming languages really start counting at 0 with good reason. It makes things a lot easier for us. There are a couple of programming languages out there, Fortran, that are horrible. Usually a programming language that starts counting at 1 isn't a very good one. Which means that the code that we're looking for is already correct because alphabet 0 is already at A. Right. So, and as I said, you can follow along to type the code in or copy and paste. No, well, I don't think you can't copy it out of there. But as you can see, it's not much typing in the first place. Right, so alphabet 0 is my A. So, and all of this works pretty cool. We've seen that the length of the alphabet is 27. Which means that the last index I have is 26, which should be the space which Python correctly gives me. That's element number 27, right? With the index, if you so want, 26, or with the code 26. Well, what happens when I request element 27? Right? Because remember, eventually we want to add things to it. So element 27 really doesn't work. It says I don't have that because I only have 27 elements numbered from 0 to 26. Ultimately, however, we want, where's my software wheel again, right? So we want the whole thing to ultimately wrap around, right? So that when I add the key here, so when I have number 25, which is the Z in this case, I add 3, I'm at 28, but as you can see here, it's mapped to the C. So 28 is 25 plus 3. So I would have to, in one of the cases, either subtract 25, which brings me to the C here, or I have to figure out something else. So let's, by the way, yes, and let's right now just let's pick a key here, right? Because if I now do alphabet 26, right, which is the space, and I want to add the key to it, I have a problem. As I said, I could check whether the number I'm looking for is larger than 26, but there is a better way to do it. One of the things that happens in cryptography all the time is part of like this wraparound problem. So in mathematics, we have something that is really very nice because so what happens, for instance, when I have, let's say I have 5 and I want to divide it by 2, right? So integer-wise, that is 2, right? And then I have, of course, a remainder, right? So 5 divided by 2 is 2 with a remainder of 1. And all programming languages, because this literally is built into the computer hardware, have a operator for the remainder of a division. We also call this the modulus. That's why this is also called the modulo operator. And so 5 modulo 2 is 1, right? Because that's the remainder. The cool thing is that the remainder of any number divided by any other number can never be larger than the divisor. This is exactly what we need here. So if I want to do the alphabet of 26 plus the key in my alphabet is of size 27, all I have to do is take that modulo 27 and I get exactly what I wanted, which is the C. This is the wraparound structure. So the modulo operator really provides this ring structure that we have here. In abstract algebra, this is actually literally called a ring. We can formalize this a little bit better here and say, okay, well, the 27 we know is the length of the alphabet. Right. And that's fine. Oops, and there is a typo. So, of course, programming languages never like when I make mistakes, and I will happily point that out. So that's the wraparound structure. And then the other thing that I want to know now is, of course, well, I know that the 26 is the space. Let's do something else here, and let's do the 25. I happen to know that this is the Z, but that's not really what I want. I want to figure out ultimately, well, what is the number for my Z? And I can ask my string, my alphabet, the question, where is the Z? Just like that. And I would get back the 25. So, and now I can actually write this transformation here for the character Z. Instead of writing the 25, I can do. And I'm going to make this a little bit better readable down the road, but that's basically how this works. So now I can plug in any thing here, right? I can plug in the A. This goes to D. I can plug in a C that goes to F, and so on. That allows me now to really write an encryption function that pretty much does what I want. So let's go back to the code and put this all together, which makes it also a little bit better readable at the same time. So in Python, we define functions with the def keyword. We like to keep it short and sweet because you're going to write these things a lot. And I call my function encrypt, of course, and it will take two things. The first thing it will take is what in cryptography we call the plain text. That's the text I want to encrypt. But at the second time, I need a key, which is the number in our case, on how many notches to rotate the wheel. All right, and then Python immediately sees that, okay, I'm starting to write the function. So all the instructions that go into the function are now indented, in this case by 4 spaces. And that's how Python knows how a function starts and how it's over. If you revert back to the original indentation, Python knows the function's over. Okay, so, and the cool thing now is that this becomes relatively simple. I started out by creating my ciphertext, which is the encrypted output of the whole thing. And at first, I'm going to start with it being empty. And now I just go through every letter in my plain text and do the transformation that we just did. And that's pretty simple in Python. It doesn't get any simpler than this. I can say for all the letters in my plain text, or for every letter in my plain text, right? I find the code for my letter, which is this one here, alphabet find letter. Then I apply my key. I add the key to the code, which is what the plus equals means, right? I just take my code plus the key, reassign it to code, and I have my new code, right? So now whatever came back as code is incremented really by the key. And now I just append, and this is also the plus equal here. I append my letter here, ciphertext plus equals, and then I just ask my alphabet. Or not ask my alphabet, I retrieve from the alphabet the letter with the code, and to make sure if the code is too large to fit into my alphabet, I do the wraparound with the length of my alphabet. And that's it. And now I'm ready for my function. So this is the loop. I do this for everyone. And now my function can return the ciphertext. And now I can actually play with this. So let's run this. And then you'll see, okay, well, nothing really seems to have happened, but encrypt is there. So it's a function that I just created. And let's do this. Let's pick a key again of 3, right? And now I can actually say, okay, encrypt. And let's do hello.
Dr. Hanneman?
Yes, sir.
In your code, what does plus equal mean?
It means that we increment that number. So in the first case, because code is a number, right? And it's actually shorthand for this. So I can actually write it like this as well. So this says, I take whatever's in code right now, add the key to it, and then reassign it to key. It's another way to say I increment code by key. So if code was 5 and key is 3, then the new code after the statement is 8, because it's 5 plus 3. Got that? And then in the case of a string, which is here, alphabet is a string, it's actually even simpler. It just appends this thing at the end. We start with an empty string, come in with a new character, and that character gets put into the end of at the end of the string. So in programming, we call this polymorphism because the same operation can have different meanings based on what you're operating on. It's actually already a somewhat advanced concept, but it's not really that hard to understand from the basic point of view, because we do this all the time. All right, So when I run this now, oh dang, I just, okay, I should have run this. Okay, let's do this again. So I pick my key equals to 3. Let's actually go ahead and already do the plain text here, and then do let's do hello. And then I can do the encryption. And voila, I get KHOOR. So if you do the math, right, HIJK, so K is the third letter after H, E is the third letter after K, L is the third letter after O, and so on. Here you already see one of the problems in this lame cipher, right? Because every letter is substituted with the same mother letter. So the OO here tells me already, oh, that's 2 of the same letters. There's not that many combinations of the same letters in the English language. So that's already a handle for me to actually start cracking the code. But that's the encryption. The decryption is actually the process in reverse. All encryption algorithms, all symmetric encryption algorithms do it the same way. Encryption goes in one direction, decryption goes in the opposite direction. Let me write the decrypt, which is extremely quick and simple. Because it is so similar, I can just copy what I have. Now, however, I come in with a ciphertext. The key stays the same. I end up with the plain text, and then I go through the letters of my ciphertext. I still have to find the letter in my alphabet. That doesn't change. Oops. There we go. And then, however, the only difference is I go in the reverse direction. I turn the wheel in the other direction, meaning I have to subtract my key. I still, however, have to append, so the plus stays here, to my plain text. And then I have the plain text. This looks extremely similar. This looks similar to the point where, why is this still complaining about it? Because, oh, here it is. I did it again. Okay. So the plain text, this looks so similar that I could actually wrap this into a single function if I wanted to. But this is easier to understand because you see, okay, it's literally the same thing with one minor difference. And of course, for the decryption, you pass in the ciphertext. Okay, so when I run this, right now we're seeing that because this is a free cloud service, that it kind of is slow right now. Let me run this. There is still do I still get an error in there? I don't understand. Let me, just to make sure, reload the page. Okay, so I've got everything back. Okay, let's run this. Okay, here we go. All right, so now again, let's do the let's do the key, right? And then encrypt. And then let's do the ciphertext. Is the encrypted version of the whole thing. So that's plain text and the key. And let's print this real quick. And now you see, okay, that's the result we had before. Let's see whether we can decrypt it. So I can do, again, decrypt, and then ciphertext, comma key. And Okay, something went wrong. Oh, that's because I still left the ciphertext here. See, this is your classic debugging thing. And you will see this over and over and over again. You will make mistakes like this all the time. After basically 35 years of programming, I still make these mistakes, as you can see. But the difference between an experienced programmer and an unexperienced one is just exactly that. How fast can you recover from this? I immediately knew what was wrong. So let's rerun this and then do this again.
The wheel still turned positive. Line 17.
Oh, okay. So it didn't. Yes, thank you very much. Obviously, it didn't catch all the changes I made to the whole thing. Okay, so let's rerun this again. Okay. Okay, and then of course the key stays at 3, and then of course ciphertext is encrypt. And then it's plain text and key. And then let's print the ciphertext. Yep, okay, that's the result that we know. Let's decrypt it. And it didn't work. Okay. Where is the problem? Let me see. For letter and ciphertext, plain text, plain text. Interesting. Oh, there it is. Of course, it did work, but I'm returning the wrong thing. I have to return the plain text. Right. Okay. See, this one stumped me a little bit longer. Again, totally normal. You will do this all the time. So yeah, let's do this again. So okay, and then plain text key ciphertext. There we go. And now for the final act, hopefully, decrypt ciphertext key, and hallelujah. All right, there we go. All right, so this is, as you can see, how this this works. And now let's just go ahead and try to break something here. So I got my encryption and decryption here, and I've got a secret message here that I have created. So I will do ciphertext here, and we'll equal that to my secret message, right? So we want to break the code. So there are a couple of ways you can look at this. This one, I think, ironically, doesn't have any double letters, so we can't latch onto that. But one of the things you could easily try to do, of course, we're going to brute force it, right? We're going to just try things. That's tedious, but relatively easy here because my key space is not large. So if I decrypt it with a key 3, as you can see, I get gibberish. Let's try key 4, 5, 6, 7, 8, 9, 10. Come on. 11, 12, 13. There we go. All right, so we just brute force cracked it by just trying all the keys. Well, not all the keys. Statistically, you will have to try 50% of the key space to actually decrypt a message, right? And since my key space is so small here because it's directly coupled to the length of the alphabet. That's not going to work. The key space for modern encryption algorithms like AES is ridiculously large. There is no way you can try, even on the fastest computers that you have, to break that by brute force. Not even the NSA can do that. The NSA used to have, this stuff used to be heavily regulated as weapons technology. I was in Europe at the time, so we couldn't get strong encryption, at least commercially, bought from a US company with more than 40 bits, because 40 bits of key space 2 to the power of 40 is already a pretty large number, is what the NSA could do at the time, brute force. These days, the NSA can probably do a little bit more. I would not be surprised if the NSA could brute force something like 64, 28 bits or something. But we're much larger than that in the key spaces these days, just to be sure. So right now we're looking at 192 bits for AES, and we're pretty certain that no computer in the universe can compute and try out and brute force the key space of that in the foreseeable future. It would still take the fastest computers on Earth right now a couple of billion years to do that. There are other ways to go about it, right? And this is what cryptanalysis is all about. One of the things you could ledge into, if you're a Scrabble player, you know that the Scrabble scores are, of course, assigned. The higher the number, the higher the score of a letter, the lower the chance it is to show up in a word. So here you can put that around and just count occurrences and say, okay, E is the most common letter in the English alphabet. So you just make a histogram and say, okay, which letter shows up first, shows up most in the encrypted string, and you say, oh, that's got to be the E. You do the reverse calculation, and then you have the key here. So this is trivial to beat, even with cryptanalysis. But of course, we have much, much better ciphers these days that, as far as we know, AES hasn't been broken yet. So that's the basic idea. This is the basic stuff that you will write in your classic introduction to programming stuff. And this is what it looks like. You already saw me making mistakes. This is also classic, and recovering from this with a process called debugging. And we will formalize that. We will train you to, of course, recognize many of these problems right off the bat so that you avoid them, but also out of carelessness, you will make them anyways. And we have wonderful tools to handle these kind of things. This is where we enter the area of software engineering on how to do the process of programming and developing large systems efficiently. So that's my part for encryption and decryption using the lamest cipher in the world. The book by Al Zweigert goes much further than that. It's a wonderful read. I can wholeheartedly recommend reading it. And as I said, it's free. All the code is freely available. You can play around with it and encrypt and decrypt stuff to your heart's content. So that leaves me with just asking for some more questions or comments. And if you don't have any, as I said, so we talked more about the theoretical side in the introduction. I'm going to do some of that as well. But ultimately, certainly when you're an introduction, when you're a junior programmer, freshly graduated, you will still do a lot of code writing. But as you mature in your career, you'll take on more and more responsibility of actually designing the software systems rather than cranking out the code, because that's what we have junior developers for. All right, good deal.
Yeah, any questions, especially from the students who are particularly interested in this? Now is a good time if you want to, revisit anything that we've covered in the last couple of hours. I think they have something to do in the afternoon as well, and that'll be another opportunity. But certainly, while it's fresh, please speak up or put it in the chat. I'll be, asking afterwards, if this is really what you want to do, and then where do you see your interests, out of these things that we've covered. And I guess, Dr. Hanneman, at every angle, these things are infinitely expandable, as we've been touching on too. So any crazy ideas, are always welcome from the students, and we'll talk through them.
There's a question from David. It's actually both, right? The interesting thing about this is, of course, government drives a lot of this, especially in the cybersecurity area, because government is interested in making e-commerce and all that kind of stuff secure, so that nobody loses money in the process. At the same time, they of course have to try to ensure security and safety of the systems that are being built. So it's both sides, right? So you can be in government and drive policy around this, and we've had particularly grad students who do a lot of that. We have a lot of our grad students actually working already in government, trying to improve their skill set, certainly around cybersecurity, because state government is right around the corner, right? So that's what we do. But yes, both ways and a lot, especially cybersecurity is a super hot topic right now. Certainly also in the light of ransomware attacks, again, e-commerce, all these kind of things that play into this. So if you're good at cryptography, you will have no problem finding a job anywhere. Video games with a group of people, or yeah, so the days where coders used to be nerds living in their mom's basement, drinking stale Mountain Dew and eating cold pizza are way over, long over. No, you will have to do this in a team. If you look at something like, I think Grand Theft Auto 4 was the first production that had $1 billion budget, and they go about it like a movie production. You have your writers, you have your coders, you have your artists who generate the artwork, you have your people who do lighting and nothing but lighting, you have your hardcore people who do the modeling and the performance improvements and all this kind of stuff. You will be working in teams of, for a AAA title, hundreds of people. And even small game studios, we have connection to a couple of indies around here in Lexington and Louisville. Even small studios are typically at least a 2-3 man team on the core, one for the coding side, one for the artwork. But even the small companies bring in lots of temporary people and interns and stuff. So you will probably not find this team, even for, as I said, small indie games, that is less than 10 people at the very minimum. So yes, it's all team-based, and we will introduce you to all the tools that you need to be effective in a team setting. I already mentioned GitHub, so version control and how to collaborate with people is a central aspect to all we do in computer science. And we'll introduce you to this as early as we possibly can, because it is so central to the process. Cybersecurity, Richard, that's more for you. I assume it's the same there, but that's certainly something for Richard.
Yeah, I mean, it's the same there. Cybersecurity, you're going to be working with teams as well, so it's not a solo career. So you've got different team members that work on different parts, so there may be a team that does penetration testing, another team that works on the policy area of cybersecurity. So it is also team-based, and that is a great question. Any more questions for Dr. Henneman? Glad to see all these great questions.
Any of us. So yeah, so, I mean, that's probably a little bit bad news for the introverts among us. And I'm typically, I mean, that's something. It's still easy luckily, it's easier to be an introvert in computer science than in other fields. But in sales, okay, I could never do sales. And the only reason why I like to talk about this stuff so much is because I love it so much. I'm usually more of an introverted person in real life as well. So it's definitely a great career if you are an introvert, but there is no way you can avoid interaction with other people. There is just no way. Systems are way too large for this these days. All right. Sounds like lunch break.
Yeah, we'll meet back in about half an hour. Is that correct?
You can call the time right now, and we'll start on that. The Zoom link is going to stay open the entire break, and I'll be here certainly 15 minutes before whichever time you say now. So if you wanted a full 30 minutes, it'd be about 35
That's
after.
about 45, yeah.
45
Okay.
after would be fine.
Okay, we'll meet 1:15. That's fine.
Yeah.
There was another question. Do these areas also require advanced degrees? Not necessarily. It doesn't. I mean, you can have the certifications and other, so it doesn't actually require the advanced degrees. I think a lot of companies also look into the certifications that are available out there and the experience in the field.
Yeah, that's definitely true. I mean, if you look at even companies like Google, this is a perennial thing. Computer science, unlike many of the other engineering fields, is still very, very young. We don't even know how to do advanced degrees well, correctly, if you so will. So many companies would happily hire you even without a bachelor's degree. That's a risk, however, I wouldn't take, because then you'd be the first to let go if the company goes under. But certainly you can have great careers with a bachelor's degree. I believe, if I'm not mistaken, Bruce Schneier was one of the best cryptographers on the planet. Has just a bachelor's degree, it's ultimately the industry is still more of a meritocracy than many other industries out there. There's no question about that. And that's ultimately a good thing, because again, nobody ultimately really in the end, when you're on a team, cares what degree you hold, as long as you can do the job and get the stuff done. All right, continue. Yeah, wow, this is great, guys. Thanks a lot.
Thank you. Looking forward to seeing everyone after lunch. So have a good lunch.
All right, thanks everybody. At 12:45, I'll be on. If you have any questions or issues, feel free to reach out to me, call me, email, or whatever. Presenters, thank you so very much. Super, super awesome, as I knew it would be. Thank you so much.